Okay, we are using theorem 2.14. We can see that if it's the nth root, we can take the nth root of the entire limit. So we'll jump over here, this example, and you can rewrite that as the cubed root of the limit of our given function, 3x squared minus 4x plus 9, as x approaches 5. So we're going to use direct substitution in here, and then take the cubed root of it. So pause it and then check your answer. Okay, and you should get 4. Okay, and the next thing we're going to look at is the sandwich theorem, most of the time known as the squeeze theorem. And so suppose you have a function f of x. Here you can see it in this light color. The graph usually really helps. And you have it's less than or equal to h of x, less than or equal to g of x. So basically h of x is squeezed in between the other two functions in an open interval containing containing c except possibly a except possibly at a. Okay, and this is an a. The copy's a bad copy. That's just saying if your limit of your f of x function as x approaches a is equal to L, and the limit of your g of x function as x approaches a is equal to L, then the one in between that is equal to L as well. Just to give it let's talk about something more basic. If I say I always eat more than Olivia, okay, I always eat more than Olivia. Let's put her over here. More than or equal to Olivia, okay? And I also make the statement that I eat less than Dane, less than or equal to Dane, okay? And then I tell you, on a particular day, I said Olivia ate 1,500 calories. On that same day, Dane ate 1,500 calories. What's that mean about me? I ate 1,500 calories because I'm squeezed in between the two of them, right? So it's that kind of idea. Same thing when we're given functions. So here we have the f of x functions that's given, and we take the limit of that. If we take the limit of our f of x, and we know it's L, and then we take the limit of a function, a different function, g of x, and we know the limit of it L is L, and the only thing I know about h of x is that it's in between the two. Okay, just like I was in between Olivia and Dame. Then the limit of that function, because of the squeeze theorem, also puts us at L. So we're going to kind of work with that. Here's a particular example. We'll battle through one of these. Limit as x approaches 0. A limit of x squared, sine of 1 over x squared, as x approaches 0 is 0. And it says use the sandwich theorem to prove. Okay, now I want you to make a note that will say since -1, let me go back to the, okay, so we're jumping back over here so I can have it. So since -1 is less than or equal to the sine of t is less than or equal to 1 for every real number t. Okay, this is a statement. We know this is the case because when we're talking about the y values of a sine function on our basic parent graph, it toggles back and forth between the range is from -1 to 1 for a basic sine function. Okay, so with that in mind, that's just your bounds for our sine function. We have our bounds that we know, but we need this to look like, what's t in this particular case? 1 over x squared, right? But we need it to have an x squared in front of that. So what can I do to each one of these? Multiply everything by an x squared, right? So if I'm going to say times an x squared, times an x squared, times an x squared, if I rewrote it and let that be my t, then what I'm looking at is going to be negative x squared is less than or equal to x squared sine of 1 over x squared. It's less than or equal to x squared. Okay, so with our squeeze theorem, it's saying let's take the limit of each of these, the limit of the left, the middle, and the right, our f of x, g of x, and see what happens with our h of x. Limit this function, which in this case is our f of x, as x approaches, what are we approaching? 0. 0 up there. We'll take the limit of x squared sine of our function in question as x approaches 0. Okay, so it's asking us to evaluate the limit of this entire function, which if we have that, we would have just 0, so that tells us no information. So basically what we needed to do is consider the limit, an f of x and a g of x to determine an h of x in the middle and see if squeeze works. So now let's substitute. What would be the limit of this particular function? The limit is 0. Good. Okay. What about over here? Plug in 0, that's just going to be 0. So if in between both of these, then what does that tell us about this function that we're not able to compute? Just 0. Okay, so by the squeeze, and that's this idea right here. So our f of x function was negative x squared. Our g of x was positive x squared, and so although it was more complicated that we couldn't see it, was squeezed in between until you're able to prove it. That's just a tactic and a method that you'll use for squeeze theorem. Okay, use theorems of limits to find the limits. In this case, we're just going to have a limit of a f of x function is given, and a limit of a g of x function is given, and it's saying evaluate this. So 6 times f of x is just going to be, what would that be? 6 times, we know what f of x is. What's f of x equal, the limit of this equal to? 5, right? Okay, so we're short on time. We're going to move through these pretty quickly. So if I take the limit of f of x times g of x as x approaches c, we can just do f of x times g of x. We know that value. This one times this one by our technique. So what can we do there? 5 times negative 1 is equal to negative 5. Okay, let's do a division one. So if we broke that apart, what is the limit of our f of x function is 5. And the limit of g of x as x approaches c is given to us as negative 1. So we're just going to get negative 5 in that particular case. Okay, remember with this, we can take the power and basically do this with it, right? Calculate the limit and then raise it to the power. So to not have to write that out, since we've done an example like that before, let's go ahead and simplify in here. So do direct substitution. 3 times 3 is 9. 9 minus 9 is 0. So really it's just 0 to the 100th power, which is 0. Okay, given this, if we substitute negative 3 in and we simplify this, we were going to get 0 over 0. Okay, so we need to do some factoring or some algebra or rationalizing. More than likely we're probably going to rationalize here, but it's not quite ready for that yet. Let's go ahead and condense this. So I'm going to leave my numerator alone. Get a common denominator. So of 3x, so if I had a common denominator of 3x, that's just going to give me 3 plus x, okay? So if I try to multiply by the reciprocal here, we're just algebraically going to try to simplify this thing a little bit better. So if I take my denominator, what's the reciprocal? 3x over 3 plus x. Then we must do the same thing in the numerator, 3x over 3 plus x. So attempting algebraically to just get this simplified. Down here, everything's going to cancel. And we're just going to be left with what in the numerator? Yeah, you're just going to be left with 3x, the limit as x approaches negative 3, and that's just going to be 3 times negative 3, which is negative 9. So reminding you of one that you're going to have